Could I have the top piece of plastic, Dave?
Here you are.
Thanks.
Here's the photomultiplier.
That clear enough?
Oh, yeah. I can see through it nicely. One of the most startling predictions of the theory of special relativity is that moving clocks run slow by a factor, the square root of 1 minus v squared over c squared. Where v is the speed of the clock relative to the observer, and c is the speed of light. For example, if we had 3 identical clocks at rest with respect to an observer, and at one moment they read the same, then of course we expect at a somewhat later time they will all read the same again. But if we have the same 3 identical clocks, but one of them is in motion with respect to the observer, then at the later time, let's say when this one has passed the others, it will reach a shorter elapsed time than the ones that are at rest. As read by the observer, the moving clock runs slow. This effect is called the Einstein time dilation, and ordinarily it's a mighty small effect because v over c for most things is a very small number, so that this whole expression is very close to 1. For example, a clock moving by us in a rocket at 5 miles a second, it loses only 1 second in 100 years. But we do have some clocks that really go fast, that go 99% the speed of light, and they run at 1/9 of the rate they do when they're at rest with respect to us. These clocks we're going to show you. These are mu mesons, charged radioactive particles in the cosmic rays. First we have to detect them. So, detect mu mesons. Then we'll stop some of these mu mesons to measure the distribution of their radioactive decay times. As you'll see, this will enable us to use these mesons to measure time intervals. So, distribution of decay times used as clock. Finally, we'll use these meson decay clocks to measure time dilation. We'll compare 2 measurements of a time interval. The measurement by mesons going at high speeds with respect to us, and the measurement by mesons at rest with respect to us. The mu mesons we'll use are produced high in the atmosphere and come shooting down toward the Earth. As they come down, some of them disintegrate in flight. The number arriving at a high altitude is greater than the number surviving to reach sea level. Right now, we're up on top of a mountain, Mount Washington in New Hampshire. We will count the number of mesons that arrive here, and then we'll go down later to sea level and count the number that survive to arrive there. By comparing these numbers, we will show that these moving clocks run slow. To start, we need to detect these mu mesons.
Every time one of those mu mesons, which Professor Frisch has told you about, passes through this special plastic scintillator, a flash of light is emitted. In fact, the plastic is scintillating right now from the mu mesons that are passing through it. We can't see them because those flashes are much too dim to be photographed. So we detect them with this photomultiplier, which is just an extremely sensitive photocell, which turns the flashes of light into usable electrical signals. Of course, when working, we have to put the plastic up next to the photocell, like that. And then to keep out stray light, we have to cover it with a light-tight cover. First, this aluminum. That's shiny to reflect the light around inside. And then, finally, with this light-tight piece of cloth. Now I can turn on the high voltage to the photomultiplier. The electrical signal from the photomultiplier comes out on this cable, which I take and plug into this amplifier. I take the output of this amplifier and put it into the trigger of this high-speed oscilloscope. So every time a mu meson goes through our plastic scintillator and is picked up by the photomultiplier, the electron beam of the oscilloscope starts moving and sweeps very rapidly across the scope face. We also take that same signal from the photomultiplier and put it on the vertical deflection plates of the oscilloscope so that the starting pulse is visible at the beginning of the trace. Most of these sweeps indicate the passage of a mu meson clear through the scintillator. This spot is where the oscilloscope beam rests until a mu meson enters the scintillator and starts the scope beam sweeping. The pulses that start the sweep are displayed over here. Notice that their heights vary. That's because some of the mesons go through just a corner of the scintillator, making a small flash of light, and hence a small signal, whereas others go all the way through. The sweep passes by each one of these major divisions in a microsecond. Right now, it's sweeping across 7.5 microseconds. Later, it will sweep across all 9 millionths of a second, which you can see. That may sound pretty fast, but one of our mesons enters the scintillator, passes clear through, and leaves in only about 2 billionths of a second, which is about 1/100th of the width of one of those starting pulses. So the width of the pulse has nothing to do with how long it takes our mesons to go through the plastic scintillator, but is determined entirely by the electronics.
Most of the mesons shoot right on through the scintillator. We can stop some of them in the scintillator, however, by slowing them down in this 2.5-foot thickness of iron. Incidentally, that's a big pile of iron. It weighs more than 10 tons. We want to stop some of the mu mesons in the scintillator in order to observe their radioactive decay.
That brings us to our second point. We already know how to detect mu mesons. Now we want to find out how long it takes them to decay, so as to use them as clocks. When a positive mu meson decays, it gives off a neutrino, an antineutrino, and one positive charged particle called a positron. When the mu meson enters our scintillator, it makes a flash of light. If it stops and decays in the scintillator, the positron makes a second flash of light. That puts a second pulse on our oscilloscope trace at the instant the mu meson decays. So now we're ready to stop a lot more of these mu mesons and measure the time distribution of their radioactive decays. So Dave, push the scintillator under the iron, and I'll get back to the scope. Let's have a look. You may notice that there are fewer sweeps than before. That's because the iron not only slows down the mesons, but it actually stops some before they can get to our scintillator. You also see that most of them still go all the way through, thus giving just one pulse. But there, did you see that one? About 2 divisions out from the starting pulse? Let's see some more. There. There. Now I want to look at the next one in a little more detail. There. That one still has the first pulse on it where the meson entered the scintillator. That meson had just the right speed to be slowed down by the iron so that it would stop in the scintillator. It then sat around for a while before it disintegrated, thus giving the second pulse when the positron was given out. The time it took the meson to stop was completely negligible on our scale. We can tell how long the meson sat around at rest in our scintillator before it blew up because we know that it takes just 2.9 microseconds for the beam to sweep from the starting pulse to the decay pulse. Now let's look at some more. There. There. You see that these pulses are occurring at different places across the face of our scope, and that indicates that the mesons take different lengths of time sitting around in our scintillator before they blow up. So if we're going to use these mesons as timing devices or clocks, we're going to have to accumulate quite a stack of data. To make data taking easy, I'm going to move the starting pulse over here to a predetermined position behind a mask on the scope face. And then I'm going to move the main trace up behind a second mask. Now, you will only be able to see the decay pulses. There. There. And there's another. These are the only pulses which we need to record. You saw the decay pulses peeking out from behind the mask. Here, let me show it to you. We're only interested in where those decay pulses occur on our time scale. And the easiest way to record that is to use this Polaroid camera. If we leave the shutter open, we can record up to about 20 separate events, one after the other, on a single exposure. We also have a photomultiplier, which looks through this aperture in the camera mount at the decay pulses. But before we can use it, I need to seal out the room light.
The light from the decay pulses that show out from behind the mask is picked up by this photomultiplier. Here's the high voltage input for the photomultiplier. This cable has the signal output from the photomultiplier. It comes up into this amplifier. It enters in the back here. The output comes out in the back here. Comes up to this circuit, which is actually a scaling circuit, which is just used as a driver for this register. This register counts individually the new mesons which have entered the scintillator, decayed, and their decay pulses have counted on the photomultiplier. If you're ready with the taping, Jim, I'll turn on the high voltage.
It's okay. Go ahead. I'll turn on the counter and open the camera shutter.
There's one. Remember, this counter gives a running record of the number of mu mesons that have stopped and decayed in our scintillator. How about, should we take 5 or 10?
Oh, 5's enough, Dave.
I'll go over and get the chart ready.
Well, here's our picture. Let's take a look at it. Here you see the pulses which are counter-recorded, all 5 of them. The starting pulse is over here just behind the mask. Now what I want to do is to measure the length of time which each one of these mesons live so that Professor Frisch can plot it on his chart. There's a convenient ruler to use, simply another exposure of the grid on the scope face. Now I'm measuring from the edge of the mask, and I find that this particular meson lived for 4.85 microseconds.
4.85. I'm drawing on this expanded scale a line representing the length of the decay time of that meson in microseconds.
Now, Professor Frisch is plotting those times vertically downwards for a reason that will be obvious later. But I don't want you to think that that has anything to do with the distance from here to here. It has to do with this distance. The length of time the meson lived in the scintillator. Now here's another one. This one only lived for 0.65 microseconds.
0.65.
And this one, 2.90.
2.90 microseconds.
This one, 0.8. 0.80.
0.80 microseconds.
And the last one, 3.45. Oh no, that's closer to 3.50.
3.50 microseconds. Okay, here are the lines showing the decay times of these 5 mesons we got. We put them side by side just to display them together, but this coordinate doesn't mean anything. It's only the time which we plotted in that direction that means something. In order to see the pattern of the distribution of the decay times, we will need to take many hundreds of counts. So, Jim, would you start an hour's run? You got film in the camera?
Yes, there's only one going. You see our first counts coming in. To show you a complete hour, we will compress time so that you will see it in the next 25 seconds. Also, we'll show you samples of the polarides which we took during the hour. $568. 2.40.
Okay.
1.65. 2, 3,
Okay.
1.65. 3.60. 2, 3, 4.
Okay.
1. Okay, here's another one. 0.65 microseconds.
0.85.
Okay, here's.
Okay.
So here's our finished chart, based on the 568 counts which we got during the hour.
The 568 counts we have plotted on our chart are the result of 1 hour's run. Previously, we had taken 5 different runs, each for an hour, and their average comes out 564, so that the 568 we have plotted are indeed a good sample of the number of mesons decaying in our scintillator every hour.
So you can think of the mu mesons as coming down in a steady rain from hour to hour. Many mesons live for as long as 1 microsecond. Fewer live for 2 microseconds. By the time we get to 5 microseconds, only a small fraction of the original number remains. And by the time we get down to 8.5 microseconds, which is the longest time we can see on the scope face, only a very few mesons are decaying.
That chart is a pictorial representation of the decay times of those mesons which had stopped in the scintillator before we began to measure their decay times. They were at rest with respect to us during the time shown on the chart. Now we come to the heart of the experiment. What happens to the decay times of these mu mesons when, instead of being at rest with respect to us, they're shooting on down by us with speeds nearly that of light? Let's look at the chart in more detail.
For instance, here's a meson which lived for 3.5 microseconds sitting in our scintillator. Suppose we hadn't stopped it. Where would it have gone? Here we are, up on top of Mount Washington, 6,300 feet above sea level. We stopped that meson up here. If we hadn't, it would have gone on for 3.5 microseconds down below before decaying. Now, how far would that have been? It would have gone a distance 3.5 times 10 to the minus 6 seconds times its speed, v. So in order to know just how far it would have gone before decaying, we need to know its speed, v.
Fortunately, we do know the speed of the mesons which stop in our scintillator because we know how far a charged particle of a given mass and speed can go through matter. A mu meson entering the top of the iron with 0.9950 times the speed of light gets just into the top of the scintillator before it stops. With any less than 0.9950 C, it stops in the iron. With slightly greater, 0.9954 C, it goes down and stops in the bottom of the scintillator. With greater speed than that, it goes on through and into the mountain. So the mesons we count have speeds between 0.9950 and 0.9954 the speed of light. For our present purposes, we don't need that accuracy. Let's just say that they have approximately the speed of light and go close to 1,000 feet per microsecond.
That is, v is 1,000 feet per microsecond, or this particular meson would have gone on 3,500 feet before decaying. Now this one, which lasted only 2.4 microseconds, would have gone on only 2,400 feet before decaying. This one, which lasted nearly 5 microseconds, would have gone on nearly 5,000 feet. I might, in fact, simply relabel this axis over here in thousands of feet. And then we can simply ask, how many of our mesons would live to reach sea level, which is 6,300 feet down? Let me put a string across here at 6,300 feet and simply count how many of our mesons would have gone down that far and reached this level. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 4, 25, 26, 27. So, if we take our equipment down to sea level, we expect to find 27, or about 27, mesons stopping and dying in our plastic each hour.
That calculation is based on the assumption that mu mesons decay, that is, keep time, when they are in flight in the same way as they do when they are at rest with respect to us.
That assumption gives us these 27 mesons per hour when we go down to sea level. But if we count appreciably more than that, say this many, it means the mesons have decayed as if only this much time has passed. In other words, we calculate this time interval for their flight down, 6.3 microseconds. They would measure this time interval.
So that's our experiment, to go down to sea level and see how many mu mesons per hour are left.
Okay, pull the cables through, Dave.
Okay, Jim, you can roll the counter under. We're down here at sea level, and the equipment seems to be in pretty good shape. As soon as I get this together, let's try to see how many mesons survived the trip down from Mount Washington. We turn on again. Boy, that was a quick one. While we're counting, let's look at the situation. We counted the 568 mesons we have on our chart up on top of Mount Washington. Now we've come down to sea level to see how many are left. Of course, we won't be able to count the survivors of the exact same mesons we counted up on top of Mount Washington because we stopped them all in the scintillator up there. Fortunately, it doesn't matter because there was nothing special about these particular mesons. Indeed, we never could have said exactly when any particular one of them would decay. What we use as a meson clock is the average distribution of decay times of a large number of mesons. So we can count the survivors of another hour's worth of mesons instead, because, as we saw up there, the average number is the same from hour to hour. We also can't set up at sea level right below Mount Washington. We'd have to excavate a hole all the way down to let the mesons through all that rock, and the Appalachian Mountain Club wouldn't like it. So we're over here at Cambridge, Massachusetts, 150 miles away, and we're counting the survivors of the mesons incident at the 6,000-foot level above us here. The average intensity of cosmic rays is the same over horizontal distances of many hundred miles across the Earth. So there are approximately 568 mesons coming down 6,000 feet above us during this hour. Now, there's one thing different about our equipment down here.
On top of Mount Washington, we used a layer of iron about 2.5 feet thick to select our mesons. But between here and 6,000 feet, there's a layer of air equivalent in slowing down power to 1 foot of iron. So to compensate, we've removed 1 foot of iron from our stack. We've removed that iron in order that the mesons, which stop in our scintillator here, have a speed 0.995 C when they pass the 6,000-foot level above us. That's the same speed which the mesons had when they entered the iron on top of Mount Washington and stopped in our scintillator. Now, this is only one of many effects we've had to take into account in this experiment. For instance, not all mu mesons come straight down. Also, a few mu mesons are produced by other cosmic rays between 6,000 feet and sea level. In addition, some mu mesons which stop in our scintillator make nuclear interactions. We believe that we've properly taken all these effects into account and that their effect on our final result is small. Now, let's take a look and see how the counts are coming in.
13. That's a lot more than we expected. Let's go on and take the full hour's count and get some good statistics. 409. 410. 411. 412. Okay, that's the hour. Instead of 27, we have 412 mesons left at sea level. That's way up here on our chart. I've been tabulating here the number of mesons surviving as a function of time on our meson decay distribution clock. And 412 corresponds to only about 0.7 microseconds. 0.7 microseconds elapsed flight time, as measured by the decay distribution of the moving mesons, divided by 6.3 microseconds flight time as measured on clocks at rest with respect to us. 0.7 divided by 6.3 equals 1/9. These mesons, moving by us at 0.99 the speed of light, keep time at 1/9 the rate they do when they're at rest with respect to us.
We've used radioactive particles, mu mesons, to show you that moving clocks run slow. But I don't want you to make the mistake of thinking that it has anything to do with the particular kind of clock we used. Equivalent experiments have been done with other clocks, atoms for instance, and the results are invariably the same. In fact, if we could only move them fast enough, we believe we could do the same experiment with alarm clocks. For instance, if a moving alarm clock passed the first of two fixed alarm clocks when all three read exactly the hour, and then 15 minutes later passed the second of those two alarm clocks, that is, 15 minutes as read by the fixed alarm clocks, then the results of this experiment make us believe that that moving alarm clock, if it had been moving with the same speed as our mu mesons, would have read only 1/9 of 15 minutes, or 1 minute and 40 seconds past the hour. Now that's how it looks to us, at rest with respect to these alarm clocks. What would it look like to someone riding on the moving alarm clock, or riding with one of our mesons? What then?
To someone riding along with a meson, the meson would seem to be at rest. First, the top of Mount Washington would come shooting up past him at 0.99 the speed of light. And then, sometime later, he would see sea level come shooting up past him at the same speed. The meson he's sitting on, when Mount Washington passes him, has some chance of surviving until sea level passes. Our distribution of decay times tells us that if he rides on 568 mesons, one after the other, about 412 of them will survive at least until sea level passes. So he reads from this distribution of decay times 0.7 microseconds as the most probable elapsed time between when the top of the mountain passes him and when sea level passes him. To this observer on the meson, the distance between the top of Mount Washington and sea level is the distance anything goes at 0.99 the speed of light in 0.7 microseconds, which according to our distance scale is only about 700 feet. So Mount Washington appears to be only about 700 feet high. Just hop a fast meson to make a molehill out of a mountain. This is an example of the Lorentz-Fitzgerald contraction, in which a moving length is contracted by a factor, the square root of 1 minus v squared over c squared, along the direction of its motion when it's moving with a speed v relative to an observer. This is just the same factor as in the Einstein time dilation. The experiment we've done can be interpreted as showing that moving clocks run slow or that moving lengths are contracted. I say clocks and lengths in order to emphasize once again that what we've done is true of all clocks and all lengths, not merely mesons and Mount Washington.